So the title is a play on words here, I guess. First of all, trying to say that Fortran is all you need for parallel programming. I love OpenMP. I love MPI. I just want them under the hood. So basically, the idea is that you can do all of your parallel programming with the features in modern Fortran, which oftentimes means that your compiler or runtime library is generating the OpenMP or MPI. You might also recognize the reference that the paper from, was it 2016 or 2017? Attention is all you need is sort of what launched the large language model era transformers. And um, so the idea here is that Fortran is also relevant in these new domains like AI. So I'll get into that in more detail. Um, One of the talks I gave this summer was at a family reunion. So I decided to include on my acknowledgments the ancestors, my parents, and if anybody's interested, I can talk about how they got me into this kind of work. But that's my team at Berkeley Lab. Lots of different open source software that we contribute to, and I'm really just listing mostly the people here that I work with the most closely, even though some of these packages are developed by a lot more people. So, quick overview. I want to start with some origin stories. I have several that I'll go through quickly. Sort of how we got here. And for motivation, I'm going to pull a couple slides from a talk that I gave a year ago to a group of nuclear scientists who were, I heard, beginning to move away from Fortran. That was sort of my introduction to the group. And so the title of that talk was "The Problem Is Not Fortran." And then I'll get into language-based parallelism in Fortran, how we do it. And we use several open source libraries that I contribute to or lead to talk about some of these different features and how they play out in practice. Then I'll conclude. So in the beginning, 1956, John Bacchus led the team that developed Fortran at IBM. And this is the cover of the manual. And I actually hadn't looked at this before preparing this talk, but on page 1 of chapter 1 of the manual, they're talking about do loops. And the reason that's significant is because there's a like when you hear the word legacy, a lot of times people expect the next word to be Fortran and they think of Fortran as old. And I would like to put forward that all of these languages are evolving and all of them are always new as new standards come out. And they're also diverging. And each is actually leading the others in some ways and maybe lagging the others in some ways and sometimes leapfrogging the others. So particularly with the do loops, I don't write loops much anymore. So if you're writing loops, which in most languages you are, you're using a technology that is 69 years old. And we'll talk about some of the alternatives today. And so in that regard, Fortran is 69 years ahead of where you are, in a sense, right? Well, let's say 35. We started to replace loops in the Fortran 90 with array statements and different things like that. Fast forward a little bit, those of you who saw the movie Hidden Figures, if you haven't seen it, make sure you go see it. It's a great movie. If you saw it, you know that the word computer was originally a job title. Mostly women held that title. And during segregation, there was a group of Black women working for NASA who, to save their jobs, basically had to learn to program because now digital computers were coming along and they had to learn how to code on the computers to do the math. And so this is a favorite scene of mine from the movie where one of the computers is checking out a Fortran book from the library. And this being segregation, they didn't want her to take it. Actually, she didn't have borrowing privileges, so she grabbed it anyway. And was actually reading it to her son. I haven't tried that. I led an after-school coding club when my son was in middle school, hoping that would interest him in coding. He's now majoring in psychology and he's an artist. But she's reading Fortran to her son and she's saying, Fortran is a new and exciting language used by programmers to communicate with computers. It is exciting as it is the wave of the future. So I'm going to contend that's still true. We'll see. Jumping forward to the 90s, the parallel programming feature set that's in modern Fortran, it takes two forms. One started off as a DSL that split off from the language, and that was called co-array Fortran. Sometimes we abbreviate it CAF. And the basic idea here was that it was developed by Bob Numrick when he was working for Cray back when they were independent. The underlying philosophy of our design is to make the smallest number of changes to the language required to obtain a robust and efficient parallel language without requiring the programmer to learn very many new rules. And I think they actually achieved that. I won't have time to show a lot of the syntax of co-array Fortran today, but I'll show a little bit, and you'll see, I think, what they mean by the smallest number of changes. John Reed, who's still on the Fortran committee and was the convener for the worldwide committee for a number of years, worked with Bob on bringing it into the language, and it came into the language in the Fortran 2008 standard. Fast forward 2008, here's a quote from Tim Matson from a paper he wrote, probably many in this community know Tim. With few exceptions, only graduate students and other strange people write parallel software. An ideal solution would automatically exploit concurrency through techniques such as automatic parallelization of loops. I'm going to say that this day has arrived, especially thanks to people like Michael and his colleague Karim Ergoui, with whom my group collaborates at AMD. Few more. This is really important because I think a lot of people have this notion of a concept of conservation of difficulty. Like if you're not doing something hard, you're not going to get the best performance. And so there's a trade-off that people usually imagine between performance and programmability. And I would actually say that's not necessarily the case. When you're using a sufficiently powerful tool, it is actually easier and you can get better performance. And so fast forward to 2011, this is a paper, one of the co-authors on it is my boss now, John Schauf at Berkeley Lab, and they were looking at charged particle code. They were comparing Corey Fortran plus OpenMP versus MPI plus OpenMP. They ran on up to 130,000 cores. Again, this is almost 15 years ago. And they got a 58% speed up by switching to Corey Fortran as compared to the best multi-threaded MPI algorithm that they had on the largest problem they were working on. And at the time, the one-sided MPI3 features hadn't come along yet. So they were looking at the one-sided MPI2 features and saying, this is too hard. The complexity required is prohibitive, basically. And so that's an interesting lesson as well. Just anecdotally, I would say that I would estimate that 90% of the MPI codes I encounter are still using two-sided MPI sends and receives, even non-blocking. And a lot of that is because the one side is a lot harder to write. So I say, why write it? One of the packages that I lead the development of is OpenCoreRays. It's the parallel runtime library for the G-Fortran compiler. OpenCoreRays is filled with one-sided MPI, but you're not having to write it because you're writing Corey Fortran and the compiler's making calls into OpenCoreRays for you. 2015, this is a paper where John Reed was a co-author, and they looked at a range of applications, magnetohydrodynamics, 3D FFTs, multi-grid with pointwise smoothers, and they compared Corey Fortran with one-sided MPI RMA. So now they're using the MPI3 one-sided features. Oh, I might have made a mistake there. I think that was a copy-paste error. Okay, so ignore the first bullet under highlights. They ran up to 65,000 cores. And they said that Corey Fortran either draws level with MPI3 or shows a slight advantage over MPI3. So you're really not losing anything, even if you compare it to MPI3, and you actually might be gaining something if you compare it to MPI2, or to the two-sided MPI, sorry. So, and of course they say, CAF code is much easier to write. These are quotes from the papers. That way it's not just, I know I'm seen as a Fortran evangelist, so I'm just giving you quotes from papers here. European Center for Medium Range Weather Forecasting, ECMWF, should be their operational model. So this was really exciting to me because this is an operational code. I've actually never, I should at some point take the time to reach out to the authors of this because I've been citing it for, a couple of years now at least. So I don't know why this work hasn't continued. Well, I guess one reason is because machine learning is taking over. My understanding is that the next version of their model will be a neural network. So they ran on over 60,000 cores. They saw speed up the whole way, no matter how many cores they were running on, and the speed up peaked around 21% at 40,000 cores. Lastly, this is a paper that I published with several co-authors. This was 2018, and we were working with the Intermediate Complexity Atmospheric Research Model, ICAR. It's developed at NCAR by Ethan Gutman. And playing with some wording here in the current era, it predicts the regional impacts of, let's call it long-term global atmospheric trends. There's a shorter term that we could use. They looked at Corey Fortran versus, so we were looking at Corey Fortran running on top of one-sided MPI using open co-arrays like I talked about. But one of the nice things is that once you have the parallel programming model under the hood, you can also swap it really easily. We were on a Silicon Graphics SGI platform, and the MPI implementation at the time was very immature. In fact, the lead developer of their MPI implementation was visiting NCAR around the same time I was, and he actually recommended not using the one-sided features in their own MPI. And I was collaborating with Alessandro Fanfarillo, who developed the first version of Open Core Arrays. He's now at AMD. And he came walking down the hall as I was talking to Ethan, and he heard that we're having trouble with MPI, and he said, "Have you tried OpenSHMEM?" And I said, "What?" And Alessandro is great to collaborate with because he sort of keeps these little things in his back pocket that he whips out at just the right time. OpenSHMEM, he said, "Oh yeah, I wrote an OpenSHMEM layer for Open Core Arrays. You can switch." So without changing a single line of source code, hypothetically without even recompiling, it could be a link time decision. You can switch your code from MPI to OpenSHMEM, right? That's the beauty of doing your parallel programming at the language level. So we also compared with the Cray implementation. We ran up to 25,000 cores, and at every data point, the OpenSHMEM was outperforming the MPI. This isn't a statement about OpenSHMEM versus MPI. This is, again, this was an immature implementation of OpenMP of MPI at the time. And again, because we were having trouble with it, beyond about 2,000 cores, we couldn't get it to work at all. So this is where it's really important to be able to make the switch so easily. Okay, so if I have all this great news and I'm saying the problem is not Fortran, so then what are the problems? One problem is perception. Most of the non-Fortran programmers mostly know Fortran 77 to 90. It just again, this is anecdotally just speaking in my experience. There's a big problem with compilers. As some of you have heard me say already, since the beginning of 2024, I've averaged about one compiler bug report a week, including this week. Actually, I reported 3 this week alone. And that's because I'm writing bleeding edge Fortran, basically. I'm using the latest features of the language. But there's also a problem with the state of the practice. Why am I breaking these compilers? Because I'm one of the only people trying these features. Because most of the Fortran programmers are writing Fortran 90 or at best Fortran 2003. Oftentimes I tell people, if you're working with undergraduates or even postdocs and you're telling them they can't use a feature that was developed within their lifetime, any features that were developed within their lifetime, that's going to be a hard sell. So, I think it's really important to look at what's happening in the language. I have a postdoc I've been collaborating with, who I had a call with a couple of months ago, where he's 35, he's 30. He was born in 1995. And he said, yeah, I've looked at it. He's working on this awesome nuclear physics code. Like they just did, Monte Carlo calculation of carbon-13. I think it's the largest, that has ever been done for this ab initio, approach. And he said, yeah, I've looked at it and I really don't think I need anything beyond, say, Fortran 95. And I said, that can't possibly be true unless you think the Fortran committee has wasted your entire lifetime. Within 5 minutes, he asked me a question for which the obvious answer was a Fortran 2008 feature that he didn't know existed. I know he's very sophisticated about his MPI, and so I asked if he was using the MPI F08 module, which for historical reasons is misnamed. It's called MPI F08, but it's enabled by features that actually didn't make it into the standard until Fortran 2018. And he is using that module. So I told him, you're using Fortran 2018 without knowing it. So what are the solutions? One solution is data. I guess Michael gave me the bad news that Fortran has slipped a little bit. This is from a couple months back. And, there was a decline. Fortran peaked in popularity. So this TIOBE index is a measure of the popularity of programming languages, and Fortran's on the bottom row here. So Fortran peaked in 1990 at number 2, second most popular language in the world. And then there was a long, slow decline out to 2020, where it dropped to 31, which, by the way, last time I checked is right where Julia is right now, just to calibrate things. Okay. But then it's recovered. And I don't know all the reasons, but I can, again, anecdotally, I can say, I think a lot of it is because there are a lot of people across all age ranges, 20s, 30s. I had a high school student in my group who was writing some Fortran with me and liked what he was saying, who are doing really, really exciting work in open source modern Fortran. I mean, one of the most exciting packages I won't have time to talk about much today is the Fortran Package Manager, which is also misnamed because it can build C and C++, and it can do it more easily than CMake or Makefiles. I contributed a Fortran Package Manager build system to a project, that Super LU. It's like 60,000 lines of C code. I only wanted it there because I was linking to it from Fortran. What I contributed was about 3 lines, plus one symlink built the entire library. And the Fortran Package Manager is written in Fortran. So it's moving into new domains. There are people doing really exciting things. Also, if you see something like this and something's really jumping in popularity, you imagine, okay, what else is growing really fast right now? Well, AI, right? And again, I don't have a lot of details, although I did just pretty recently see an article where someone was saying they're using Fortran for their AI algorithms, and I'm going to show you how I'm using them in AI algorithms. And it's great. It works out, really nicely. Okay, those are that's all the background origin stories. Let's talk about the parallel programming. The latest standard is Fortran 2023, and there are mainly 2 feature sets I would talk about. Although in my mind, I'd say there's a third, which is why I have 3 of the major bullets here. So there's what are called the multi-image features. So this is SPMD style programming. So this is like writing MPI, where instead of rank, we say image. So an image is essentially a copy of your program. Each one runs asynchronously unless the programmer does something to synchronize. There's also a partitioned global address space, which basically are distributed data structures. We call them co-arrays. Essentially, you get 2 sets of subscripts to index through the array. One goes in parentheses, which is how Fortran traditionally wrote its subscripts for arrays. The other goes in square brackets. With the first set, you're indexing through local data, and with the other, you're accessing remote data. There you go. You've been trained in writing co-array Fortran. It's pretty straightforward. Do concurrent is the more fine-grained loop-level parallelism, and it can be used to program CPUs or to run on GPUs. And there are multiple compilers now that can actually offload do concurrent to GPUs. The NVIDIA compiler can do it, the Cray compiler can do it, the Intel compiler can do it, and pretty soon flying with some help from AMD. So some things I'll say about it. Dan Nagel, who passed away a couple of years ago, but he led the US body of the Fortran committee. And he said the philosophy of Fortran is to give the programmer the ability to communicate properties of their code, like these iterations are all independent, there are no data dependencies, rather than mandating specific optimizations that the compiler use to exploit those properties. Another thing I'd say about do concurrent is that it's syntactically and semantically collapsed, meaning you don't need to tell the compiler to take your nested loops and collapse them. And so what you see here may look kind of nested because I've got 2 indices, 2 loop counters that I'm ranging over, but there's no implied ordering between the iterations in this loop in either I or J or between them. We have locality specifiers to say this data is local to this iteration or it's shared across iterations. And since the 2023 standard, we also have what we call reduced locality. We can do reductions. I would also say there's a bunch of implicitly parallel features that aren't being fully exploited just yet. Things like array statements, which by the way can be multidimensional arrays, and elemental procedures with an elemental procedure. And this is actually a Fortran 95 feature that actually that's the crazy thing. When I say most Fortran programmers are writing Fortran 90 or 95, they're not even using a lot of what was in 90 and 95. I talk to people all the time who write Fortran all the time who don't know what elemental procedures are. For an elemental procedure, I write it so that my arguments are scalars. but then I can pass in an array. If it's a function, the compiler will apply that function to each element of the array and give me an array result. It's a beautiful feature that gets rid of so many loops for me. Think about how many times you write a loop just to, traverse an array and do the same thing on each element. All that collapses to one line once you have elemental procedures. Okay, throwing a wall of text at you here. Obviously, I don't expect you to read everything on this wall. The goal of throwing this much at you is to come at you with overwhelming force and convince you that it is a big feature set. We're not just talking about a few things that got added to the language. One frustration I have is that even amongst people in the compiler world, they kind of tend to see the parallel features as just an appendage or appendage that got attached to the side of the language. It is a massive feature set, with various synchronization mechanism. Events are basically encapsulated atomics that you could use as semaphores. Notification mechanisms where I can send data to another or put data on another image and also at the same time notify it in one statement. Teams, which is something similar in MPI. Various functions, collectives, atomic subroutines, lots of stuff. And it's growing. The next standard, we're code naming it 22Y, where we've been hoping Y would be an 8, but I'm thinking now it's probably going to be a 9. We'll have non-blocking collectives, asynchronous collectives, where you can launch a collective and then check later whether it's complete with respect to the image that's running. We'll have collectives that you can do just within a team, a subset of images. And we'll have a better marriage of object-oriented programming with these parallel features, so you can have polymorphic co-arrays. And just as a side note that's not related to parallel programming at all, so this is a slight tangent in the talk, but I'm just really excited. There's a great generic programming feature coming along, which is type-safe templates. So what happens with type-safe templates is that you're able to state requirements in your template, and requirements are abstract relationships between types. You're saying things like, if I add a type T to a type U, I'm going to get a type V. So now the compiler can do type checking in your algorithm, in your template, without knowing the types. So you can get good error messages on the template itself before the point of instantiation and long before the generated code. And we'll have a standardized Fortran preprocessor finally. So lots of open source software that my group develops that I can talk about to sort of put some meat on the bones in describing all these different technologies I've been talking about. This first one actually is not software, it's an interface. And the idea of the parallel runtime interface for Fortran, PRIF, is that it's a compiler agnostic and runtime agnostic interface that supports the multi-image features for compilers. So any compiler that targets PRIF can use any runtime library that supports PRIF. So things become swappable. And we're, of course, working on the first implementation of PRIF. That's what Caffeine is. I think that's the next slide. So one of the things that's radical about this is it's not just a parallel runtime interface for Fortran. It's also mostly written in Fortran. If you go to GitHub, I think it'll say like 49%, but that's actually not quite right because we're vendoring a memory management, memory allocation library that brings in a bunch of C. I think in terms of the code that we wrote, it's probably more like 80% Fortran. So we wrote the parallel runtime library for Fortran compilers in Fortran. Again, Fortran moving into new domains that most of you probably wouldn't be aware of. There's a simple one-to-one relationship in many cases between features like num images tells you how many images you have running. That's a function that's in the language. So the compiler would generate a call to PRIF num images. Similarly, if you're allocating a co-array, so this is where I was talking about earlier that you'd have two sets of indices. Here I'm just showing one dimension. So that's where I have the n for xn and one codimension, which I'm not specifying. So that would be whatever goes inside square brackets. And so that's one of the things that's really nice with this approach also is that if you don't need to access remote data, in many settings, most settings, you can drop the square brackets. So that makes it really easy to parallelize legacy codes. You only add the square brackets where you need to do communication. So it also makes it really clear when communication is happening. It would really hurt performance to have communication happening, in unobservable or not clear ways to the programmer. But you could actually have up to 15 dimensions total. You could have 7 regular dimensions and 8 codimensions. So when you allocate, allocate is a statement in the language, the compiler will translate that into a call to PRIF allocate coarray. So you can see what the stack looks like over here. And we work at a lot of levels in this stack, including we developed GasNet in my group, which you can think of as being similar to MPI, except that GasNet is always under the hood. You'll never see calls to GasNet in applications. Caffeine is the Corey Fortran framework of efficient interfaces to network environments. Took the liberty of using the hyphen there. That's how Bob Numerick originally spelled coarray, but in the standard it doesn't have a hyphen. And as I mentioned, Caffeine is written mostly in Fortran. We're using the non-parallel features of Fortran 2018 to support the parallel features of the language. So basically that gives the compilers and developers a migration path where if you support the non-parallel features first of Fortran 2018, we'll give you the support you need for the parallel features. Caffeine builds on top of GasNet, EX, where the EX stands for exascale. And a lot of text here, but the main thing is just to look at that last column. Most of it's done. So this is mostly implemented. Now the process is upstreaming things to the main LLVM project repository. And we just got the first few commits in there over the past few weeks, which means at least the collectives are there now, and synchronization mechanisms and things like this image tell you which image you are, num images to tell you how many images are running. And that actually is sufficient for a surprising number of applications, sort of the embarrassingly parallel applications, including some that we develop. One of the packages I mentioned on an early slide was Julian. It's a correctness checking framework. You use it to write unit tests or assertions in Fortran programs. And all of the features that Julian needs are now supported by LLVM Flang. Just again, as of the last few weeks. So the most recent release of LLVM Flang was closer to 2 months ago, and that's 21. So the coarray features, the multi-image features are not in that 21 release, but they will be in 22. And if you build LLVM Flang from source, you can access, some of these features now. And we're working closely also with another company, Cyperl. It's based in France, and they're working on the lowering, basically taking the multi-image feature syntax and lowering it to MLIR. And right now, a lot of their activities on developing a new MLIR dialect for multi-image features. So we have a paper that Etienne Renaud from Cyperl will present at the LLVM workshop for HPC, LLVM for HPC workshop next month at SC25. And in that paper, we're doing some things like distributed memory runs. So the cool thing is I haven't gotten into much detail on do concurrent yet, but the automatic parallelization of do concurrent is actually there on CPUs, is actually there in the 21 release, thanks to Karim Ergoui, Michael's colleague at AMD. And so you can actually run a program now so this is actually the first open source compiler that had both of these capabilities. G-Fortran could do the multi-image features, so you could run a distributed memory, but it wouldn't automatically parallelize do concurrent. So now if you build the current main branch of the LLVM project, you can both run a distributed memory and automatically parallelize do concurrent on CPUs. And so here, basically on the left and right, the reason those plots mostly look the same is because we're basically showing that we get the same performance as the most mature Corey Fortran implementation, which is the Cray compiler, because Bob Numerick was at Cray when he invented Corey Fortran, right? So mostly the same in terms of performance. This is a plot of bandwidth, I think. Fiats is a deep learning library that we developed. That you can expand that two ways: functional inference and training for surrogates, because we support a functional programming style, or Fortran inference and training for science. And Fiats is also all Fortran all the way down. And I'll show you what it looks like to implement some of the most important algorithms in deep learning using modern Fortran. Works out really well. So it's 99% Fortran. And one of the things that you get, so what does that buy you? So sure, on the implementation side, it buys you a lot, but what about for users? If you look at, if you're writing Fortran and you want to call a deep learning library, I see two categories of options right now. There's a few, I know of three APIs, Fortran APIs to C++ code, like libtorch, which is the backend for PyTorch. And then I know of three others, including Fiats, that are all Fortran all the way down. One of the things it buys you is that we write our procedures so that all the procedures are declared pure. Fortran 95 feature, again, one that most Fortran programmers aren't using. One of the benefits, so there's all kinds of optimizations the compiler can take advantage of when you write a procedure as pure. That doesn't necessarily mean you go slapping pure on your procedures and suddenly everything's going to speed up. Because in many cases, if the compiler is smart enough, I know that in the case of G-Fortran, the compiler will try to detect if your procedure could have been declared pure and mark it as implicitly pure. So a lot of the analysis can, so it's kind of like Michael Pollan wrote a lot of books on food, and he had a lot of interesting things that he did in like his third or fourth book, where he was kind of summing up his philosophy on food. And he was also talking about supplements. Apparently, most studies show that supplements don't actually make you healthier, but most people who take supplements are healthier. But it's a spurious correlation because of the same people who get exercise more, eat right, right? So you don't necessarily need to put pure on your procedures, but write your procedures as if they were pure, right? So Michael Pollan says, you don't necessarily need to take supplements, just strive to be like the person who takes supplements. I say the same thing about pure. But we do actually add the pure keyword. And the reason we do is because there are some important restrictions. The most important one, well, one is that if someone else is writing a pure procedure, they won't be able to call our procedures if ours aren't pure. The compiler will enforce that. Okay. And that is difficult or impossible for the compiler to enforce if the underlying procedures aren't Fortran. Because there's a page and a half of constraints on the keyword pure in the language, and the compiler needs to check all those. More importantly, especially for this audience, is that if you call a procedure inside a do concurrent construct, that procedure has to be pure. It's part of the language standard. So if we want people to be able to call into our library and take advantage of automatic parallelization of do concurrent, our procedures have to be pure. And again, it's going to be difficult or impossible to do that if you're just writing an API that's backed up by C++. So this is what it looks like to do inference with Fiats. Basically here I've got a neural network object. In Fortran, the percent sign is like a dot or an arrow. So it's how I invoke a method on an object. So I'm invoking the infer function on my neural network object, and I'm passing in inputs. And so these inputs are objects, and it's a three-dimensional array of objects. So that's why I've got the IJK indices. I'll get that result and I'll assign it to an outputs array. So traditionally what I would do is I'd write nested loops, right? And keep in mind, loops are inherently serial, like they need to be. What if your loop is a time advancement loop? You have to respect causality, right? So you need one iteration to happen before the other. So the way programming has developed over time is we write this 70-year-old technology that is inherently serial, and then we come back and say, oops, I lied. I don't really want you to do these sequentially. I want you to do them in parallel. And, oh, I didn't really need to nest all these loops. Please collapse them for me. What I'm suggesting is, why not just use a mechanism that is syntactically and semantically collapsed from the beginning, and syntactically and semantically parallel from the beginning, where I'm communicating to the compiler. There are no data dependencies between passes or iterations of this construct. So that's what it looks like to do the same thing with do concurrent. Better yet, I really want to live in a world where I can take advantage of the fact that my infer function is elemental. Remember, with elemental, even if I have a 3D array of objects there, I don't need to loop or even do concurrent around them just to traverse the array. Because it's elemental, I can just pass in the whole array and I can get an array result back. So I really want to work towards a world where I can get that to parallelize. Right now, this will work. It will give me the right result, but even with the OMP work share there, it won't parallelize just because the compilers haven't advanced to that point yet. So this is what it looks like if we compare the automatic parallelization with do concurrent using Fiats on a neural network that was trained to predict aerosols in the atmosphere. So this is from a paper that I presented at ISC with Michael and Kareem as co-authors and others at Berkeley Lab with me, Jabé, Dan Lucia, Catherine Rasmussen. And I forget which is which, but on one side, you're seeing the actual calculation, the physics-based model, and on the other side, you're seeing the neural network. And the good news is you can't really tell the difference. And running on a single node of NERSC's Berkeley Labs Perlmutter supercomputer, we're getting, basically the same performance with automatically parallelizing do concurrent versus writing the do concurrent ourselves, which you saw on the previous slide. Switching from, so inference is easy. It's like maybe 20 lines of code at most. Well, fortunately, because Fortran has matmul, right? Matrix multiplication, that's part of the language. Training is more challenging. And both do concurrent and the multi-image features first came into the Fortran language in 2008, but the parallel features expanded greatly in 2018. With regards to do concurrent, we added locality specifiers that I talked about earlier, local, shared, things like that. And in 2023, we added reduce locality, which you can see, in the upper right there. So that allows me to do a reduction. So this is basically one statement that the ampersand is a continuation character, and that this is just a statement label. It's my version of a comment, basically. And so right now we're, since the compilers are advancing, transitioning, we have sort of 3 blocks at the top of our training loop inside Fiats. If we have Fortran 2023 locality, we're golden. We basically start off with just one statement. If we don't have reduce locality, we drop back to, let's call that 6 statements with Fortran 2018 locality. Or if we go all the way back out to 2008, where there was no ability to specify locality, we're out to, let's call it 8 statements, something like that. So there's a nice reduction in complexity from being able to do these things in the language. There's a lot of other benefits. I'm thinking now of one of the posters I saw here at the IWOMP workshop that's talking about MPI data types. Whoever that is, I wanted to talk to you, didn't get a chance to catch you in front of your poster. This whole business of like, how do we shove our data types through MPI, all that stuff goes away if the parallel programming model is part of your language. It knows all of your data types, including the ones that you design yourself, So there's a lot of simplicity from having these features in the language. Another wall of text. Even I can't read this one, and I'm only a few feet from the screen. So the goal here is just to point out that that is our entire training loop. It's about 96 lines of code. That does stochastic gradient descent with the Atom optimizer. So, pretty close to state-of-the-art training of neural networks in 96 lines. If you took that same thing and translated it, I hear so much these days about translating from Fortran to C++. And one of the things that concerns me about that is that, again, as I said at the beginning, languages are diverging. They don't have the same capabilities. C++ only just got multi-dimensional arrays recently and still doesn't have array statements. And if you look at our training loop, it is deeply nested with do concurrent, and pretty much every line is a multi-dimensional array statement, right? Where we're updating the weights and biases in our neural network. So when you see the colons there, so like DCDB, that's the gradient of a bias. And we're saying we want elements or rows 1 through n, where n is an array itself, and then we've got rows and columns in it basically. And if you took, so again, each of those lines 88 through 91, each of those is a 2D array statement, which means every single one of those gets expanded. Well, maybe that's not the way to look at it. Maybe not every single one of them. Anyway, point is you're going to need to unroll this if you don't have array statements. If you don't have a parallel construct like do concurrent, Michael has shown me what it looks like to do it with C++ using lambdas. I think lambdas are cool. They're wonderful. This is much easier to write, especially if you're new. I've done a lot of teaching. I can take students. I used to teach a graduate course. I taught 3 times at Stanford, where I could take students sometimes who had no Fortran experience, and Stanford's on quarters. And in 12 weeks, I could have them writing object-oriented parallel code, to solve, differential equations, right? And it's only because of the expressiveness and the simplicity of being able to write code like this. So I would guess that by the time you unroll your loops, add OpenMP directives or what have you, this 96 lines of code could expand by a factor of 5 to 10 at least, if in most other languages. So that's AI, and I think I've only got a couple minutes left if we want to leave time for questions. I'll just mention that also doing a lot of work. Kind of wanted to put the AI first since that's the hot new thing, but we're also doing a lot of work with traditional HPC problems, like solving partial differential equations. And one of my goals for a long time has been to try to make it so that I could write the differential equation in code in a form that resembles the way you would write it on a blackboard, and have that run in parallel in distributed memory and offload to a GPU. And when all that happens, I can retire. I think it's not too far. I'm 58, so it's got to happen soon. I think it's going to happen. Anyone in the room recognize this equation? Usually I'll get at least a couple people. Anyone have a physics background or mechanical engineering or aerospace background? Know what the equation this is? This is the incompressible Navier-Stokes equations. And what I would submit is that it's pretty close to how you would write them in a textbook on a blackboard. This is compilable Fortran syntax at the top. In Fortran, you can not only overload existing operators like you can in C++, you can also define new operators. That is really important in terms of the expressiveness of your code. But the best thing is that those can be pure, which gives you a lot of guarantees around being able to do the whole expression evaluation asynchronously. And even better is that those can be distributed objects. So what you're really looking at is something that drives a lot of computation. And so even though it wasn't familiar to anyone in this room, if you were to take someone who just took their first course in fluid mechanics and they'd seen the Navier-Stokes equations in a textbook, they probably would recognize that. Versus if you walk them over to most computational fluid dynamics codes, they wouldn't see anything on the screen that looks even remotely familiar. So this is my dream of like where I want to get things. So far, I'm at the level of doing it for the heat equation or the diffusion equation. And that's what we're doing it in this matcha application. And so this is just kind of showing what it looks like to do time advancement in matcha, and how we're doing things in 3D with grid partitioning. And basically, this is showing that in that code that's running in distributed memory, ultimately it turns out that the do concurrent is the bottleneck. So that's why we really need to offload it. Julian, as I mentioned, is our correctness checking framework, and it's also our first user of the multi-image capabilities in Flang and Caffeine. So you can now do parallel testing using the native features of the Fortran language. This is what it looks like in Julian when you're writing a test or an assertion. You guys, who knows the term vibe coding? You guys heard this term, natural language prompting of an LLM. So Julian is providing idioms, like statements that you can make that read like a natural language sentence, but are actually backed up by the formal syntax in a standard and precise definitions in the software. And so we're calling it idiomatic vibe coding if you include some Julian tests in your prompt. So, in this statement, TF approximates TP within tolerance. Approximates is an operator. In Fortran, when you write your own operators, you bracket them with dots, and within is an operator. And so Julian will take that and do what you might imagine, take the difference between the two and see if the absolute value is within tolerance. Also, really, hopefully, those are actually 3D arrays. All the operators in Julian are elemental. So you can pass arrays into them. And what will happen is if your check goes through, then your test passes, everything's fine. If not, you'll get diagnostic messages only specifically on the elements that failed the test. So lastly, this is just some code I got from Michael while we were here this week, doing Saxby with lambdas and sort of like what would be the alternative to do concurrent. I think if we were writing C++, it's been a long time since I've written C++. I did write a 2D Navier-Stokes solver in C++ when in grad school, and had lots of C++ in the book I published 15 years ago, but not recent enough in my C++ to have much experience with lambdas, only a teeny bit of experience. So I'm going to take under advisement from Michael that this is the equivalent to the do concurrent. I would say the other stuff is a lot easier to write. And I know it can be hard to convince young people to take a look at Fortran. I would say a big part of the problem is the Fortran that's out there. When I show young people the new ways to write this language, they get super excited. So Fortran 2023 offers a native parallel programming model that supports execution and communication in shared or distributed memory, and offers automatic parallelization on CPUs and GPUs to exhibit comparable or better performance to alternatives across a range of applications. I showed you guys a lot of cases here. There's tons of people who will try to say, oh, they're making this stuff too easy, it's not going to perform well. I showed you the papers. I'll give you my slides. The AI isn't going to be as good at writing the modern Fortran. I would say I'm pretty impressed though. It can do pretty well. It just doesn't nail it. Like they still need to tweak things some. For all I know, that might be true in most other languages too. But so we have a paper that we wrote this summer that looked at what happens if we give it Julian tests, and try to get it to write some really advanced Fortran on a not so advanced algorithm. So basically that diffusion equation solver, if you're using central differences, this is something that, a first-year grad student, second-year grad student would write without much trouble. And only one of 4 AIs that we used actually even gave us compilable code, even after a couple of iterations. And even that one didn't pass all of our tests. So it does better than I had hoped, but, it still hallucinates.
Also, one question down here. You have one?
Yeah, one question about having all that baked into the language. I'm a bit like reluctant to that idea because like as you told, you don't know when the next version of Fortran will actually come out, and like doesn't that limit the capabilities in a sense that you have to wait for a full language standard release and you're introducing additional complexity to the language for things that could be a library feature, like for example the do concurrent. So for example in Julia you can do similar things, but you can do them by extending the language with libraries, and libraries can evolve a lot faster and introduce ideas a lot faster than having that baked into the language. And then maybe if you like bake the wrong things into the language, then you might break the language at some point and it gets more complex.
Yeah, and that has happened. I mean, before the features I talked about, there was there was a DSL called High Performance Fortran and HPF, I think, and it had a parallel loop called for all, and that was in Fortran 95 and has since been declared obsolescent and is discouraged from use. So and even with do concurrent, there's at least one very influential and sharp compiler developer at NVIDIA who says do concurrent is broken. And what he's getting at is that you can there are legal do concurrent loops you can write that will not give you the right result in parallel, right? So in that sense, it's under constrained, I guess, but I'd rather that to being over constrained. Basically I saw I had like default none on there, which basically forced me to specify locality for my variables, and if I do that, I know I can, get it right. And so it's a tough balance. And I do like what you're saying, the idea that you can grow with libraries faster. And I'd like to see more of that in Fortran too. So I think we need both.
Thanks a lot for the talk, and it's nice to see that, especially for the flow equation, it's making much more out of its name than ever, I guess. So my question would be a bit different about tooling. So you have a lot of layers, like you're on top of MPI or OpenMP, and also with OpenMP with the parallelization. So how would I, as a performance analyst, take the problems when it's coming to performance bottlenecks? So the user can express stuff really easily, but if it's coming to the expert level, getting out the last pieces of performance on an HPC platform, what possibilities do I have here?
Well, I think when you talk about getting the last bit of performance, I think you're assuming, sophisticated programmers, right? And I certainly would never argue that a really sophisticated programmer should abandon OpenMP or CUDA, or OpenACC or what have you. But so I would think about like what I said earlier about MPI. Most people I meet, like domain scientists, physicists, chemists, engineers who are not computer scientists, if they've looked at the one-sided MPI, well, first of all, some of them have never heard of it, or if they have, they've looked at it and ran away screaming, or they tried and couldn't get it to work. So you've got about 10% of people who typically are computer scientists, either by training or by trade, who can get that stuff right. For the rest, they'll actually get a speed up by switching to Code Fortran because it'll generate one-sided MPI for them, which would be better than the two-sided MPI that they were writing. So it's a question of who's doing the programming, I guess.
Thank you for your talk. I've been coding Fortran for 50 years, and I feel quite impressed about all the things I've missed. Now, my question is about your discretization of the diffusion of a heat equation. You took a physical grid based on finite differences, but there is an alternative which is used in weather model spectral function methods. You don't actually deal with a physical partition of the grid, you partition over functions, but you end up doing matrix vector operations anyway with that. So just want to point that out. But right, I have to get with you about getting back into code and Fortran. Thank you. For
awesome. Good. Yeah, I have experience in both areas. My dissertation code was a spectral code, and I've worked with spectral codes, or wrote spectral codes for years after that. The latest thing I'm really excited about is called mimetic discretization, developed by Jose Castillo at San Diego State University and his colleagues. I just last night at midnight got my first mimetic discretization working, which left me a few hours to work on this talk. And with mimetic discretizations, they use a staggered grid, and so you're guaranteed conservation properties. And Jose refers to it as a discrete calculus. So you get a discrete version of Gauss's divergence theorem and Greig's theorem and that sort of thing. And so that's kind of where, and that's what I think would work best with the approach that I was describing. Well, spectral methods do as well too. So my earliest versions of what I showed with that form of the equation were written with spectral codes. There were a few cases where it ended up being a little bit awkward because there's something I really want to do in spectral space that doesn't look the same in code as when I'm doing in physical space, but works pretty well.